Okay, how's everybody today? Good, all right. Well, we're almost done. We're a couple of days out from the end of the first 6 weeks, so we are 1/6 of the way through the school year. Okay, so only roughly 30 weeks to go, not including holidays or anything like that. So it's shrinking. So there's always, the glass is always half full. But just a couple things. Remember on Friday, the last day of the 6 weeks, we'll be taking our district assessment. And did I talk about the extra credit coming from the district assessment? I did not. Okay. So yes, okay, so I did mention that. Good, good, good. So on Friday, we're taking our district assessment. It's 20 questions, multiple choice, except for the one that's open-ended. It's going to have inverses on there, compositions of functions, a little bit of even and odd functions, and I'll kind of remind you about that tomorrow just before you go ahead and take it. But overall, I don't think it's too terrible of a test. I always tell my students, don't worry about the district assessments. It's not counted a lot. I'm going to curve it. But as far as the extra credit goes, before the curve, if you get 12 questions right, okay, just 12, get a 60 or above, I'll go ahead and put 10 points on that test that we just took Monday. Okay, and if anybody did score high enough, the maximum has to be 105, unfortunately. But if all the points won't fit on the test, I can always put that on some other grade. Can always boost the average a little bit. All right, so we should be able to finish today and tomorrow. And don't forget on Thursdays, we have that young woman, Landry Stern, with us. So she'll be here tomorrow. I'll see if I can encourage her to get up and maybe interact with you guys a little bit more. So we'll see what happens. But all right, let's talk about some inverses. So when was it yesterday, correct, that we started these? Okay, so if you have those notes, let's go ahead and get those out. If you need extra copies, I got them right over here in that little filing cabinet on top of the cart by Adolfo. All right, there should be 3 papers. So we started yesterday talking about inverses. Now, if I want to find the inverse graphically, what's the line of symmetry that I reflected across? Y equals x. Yes, it's the linear parent. Okay, now I'm going to show you a little trick with that once we get to our first graphs. But if you reflect across there, you're going to get a inverse. Now, the thing about inverses, we really like our inverses to be functions. If it's not a function, we just call it an inverse relation. So one of the last things I'm going to do is show you if you know that your inverse is not going to be a function, how to restrict your domain. And it sounds worse than it really is. So here's our notation. That little -1 indicates we're talking about an inverse. So whether it's F inverse, G inverse, whatever. So the basic idea is to go ahead and take the x's and the y's and do what with them? We're going to switch them. The x values become the y's and the y's become the x's. And we talked about a point here yesterday like -1, 2. On the inverse, it would simply be 2, -1. That's all you do is reverse it. And that's what happens to the points when you reflect it across y equals x. Well, then we also talked about this idea of 1 to 1. Okay? And we use a horizontal line test to determine if that's going to work or not. So what does it mean 1 to 1? What does that refer to? Okay, what's that? Well, it goes along the line. It tells me whether the inverse is going to be a function or not. Because let me take a step back for a second. And I'm going to use the mouse here because that's been working a lot better than my trying to get the bar. So let me move these over to the side. So we were talking about this yesterday, and I'll kind of just go over it again to make sure we're making the connection. But take a look at this parabola. It opens up, right? Okay, domain is infinitely wide. If I take a vertical line, and I start sweeping it back and forth. Okay. Is he a function? Yes, he passes the vertical line test. Now he fails and is not a function if the graph touches the vertical line in 2 or more places at any time. So what this is telling me visually is that there are no values of x that do what? That repeat. No values of x repeat, okay? So the same idea is going to apply when we're talking about the horizontal. So if he passes the horizontal line test, he is 1 to 1. If he fails the horizontal line test, he is not 1 to 1. Well, the vertical line test tells you if any value of x repeats. What's the horizontal line test tell you? If any value of y repeats, yeah. So you'll notice this guy right here, we've already got him listed not one-to-one, because you'll notice there's a lot of places where I am hitting the graph twice, okay, with that horizontal line. So this is not one-to-one. But why is this important when we're talking about inverses? Brandon, what can that tell me about the inverse? That's exactly right. Brandon says because you have to switch the x and the y values. And if you have repeating y values and you switch those, the repeating y values suddenly become repeating x's. So we can tell, looking at a graph, if it's one-to-one or not, if the inverse is going to be a function, okay, yes or no. So we can already tell whether we're going to need to restrict our domain or not. Okay. And let's go ahead and get to some examples here. All right. Now you'll notice this graph is not perfect. I had to stretch this a little more to make it fit the screen. So this line of symmetry here, y equals x, is not hitting exactly the points that it needs. So, just kind of bear that in mind when we're going through this example here. So y equals x. Now we've got this curved graph here. Looks like the top of a parabola. So it says for each of these, draw the line y equals x. Well, we already got that. Sketch the inverse of the function on the same grid. Which of the functions are one-to-one? Write the equations for each of the functions from the graphs, and then find the equations of the inverses algebraically. Well, let's go ahead and call this guy f, because f of x is the most common name that we use for a graph in mathematics. Okay, so I've got some bars over here already, so I'm going to take this. Let's start with the vertical. If I move the vertical line back and forth across this curve, what do you think? Yes or no? Is he a function? Does he ever touch it in two or more places at once? Now remember, we're not comparing it with the y equals x. That's just my line of symmetry, just the curve, just the curve. So if I move it back and forth, it's never touching it in two places. So he is a function. Well, let's see, this same curve right here, okay, is he one-to-one? Yes, he's never hitting that graph, the horizontal, in two or more places at any time. So I already know f is one-to-one. So what does that tell me about his inverse? It should be a what? It is going to be a function. Okay, so the inverse is probably going to look something like this. Okay, it's going to curve upward like that. Okay, and you can tell if you go ahead and use the horizontal line test, the vertical line test, he is a function and he's also one-to-one. And kind of excuse my graph. I'm not the best artist in the world. Remember, I said the graph wasn't the best to begin with. But this one that I drew right here, this would be f inverse. So let's say that's f of x and that's f inverse. Okay. Well, let's go ahead and write the function. Can anybody tell me what parent f is based off of? What parent looks like half a parabola? Oh, not x cubed. You're in the ballpark though. Genevieve? Oh, not squared. What's that inverse? Square root. There we go. The square root of x. Okay. Because remember, the square root of x, he starts here at the origin and then he just curves up to the right. He looks like the top half of a parabola that opens sideways. But it looks to me like he's been shifted in two directions. From the origin, how far left and how far down? 3 left, 2 down. So there's no dilations here. These are just shifts. So f of x equals, we got this square root. So would that be x plus 3 or x minus 3? Wait a minute, plus, and we're going left. When you're adding or subtracting to x, you take the opposite. So this is plus 3. And what about that 2 down? Minus 2. There you go. And he would be outside the radical. All right. And we already know a couple things about him. We said that he was a function. And we said he's one-to-one because he passed the horizontal line test. Okay. Well, what I want to do is come up with the equation for this guy. Okay. Now, before we do that, let's think about f's domain. How wide is he? There you go. He starts at -3 and he goes all the way, right? Okay, so I'm going to take this off. So let me write the D for domain. So his domain goes from -3 all the way to infinity. What about his range? How low does he go? Looks like -2, again included, and it continues slowly, but it is going to go all the way up to positive infinity. So -2 all the way to infinity. Okay. Now, let's go ahead and separate this. I want to go ahead and figure out what his inverse is, the equation for that other graph that I just drew. Okay, does anybody remember from Algebra 2, how do I do this? Hey, what's up? The domain and range are going to flip. Okay, so this domain becomes the range of the inverse, and that range would become the domain of the inverse. Now, Angel, you were saying something about solving for y? That is absolutely right. If you want the inverse, you switch the positions of x and y, and then you solve for y. Now, we're looking here, remember that f of x, that just means your y values, so they're interchangeable. Okay, so we just switch their positions in the equation. So instead of y equals, I'm going to say x equals the square root of y plus 3 minus 2. Okay, you switch the positions of x and y, and then you solve for y. What you get should be the inverse. Okay, now we know this one is going to be an inverse function. We already knew that was going to happen. Okay, so how do I solve for y? What do I do first? Okay, let's add the 2. So now it's just manipulating an equation like we've done before. So if I add 2 to both sides, those opposites cancel. So x plus 2 is equal to the square root of y plus 3. Well, now what? Okay, to get rid of the square root, we have to square. But since I have a binomial over here, I'm going to square that quantity. Okay, square both sides. So the square and the square root cancel. So I've got x plus 2 squared equals y plus 3. And our last step is to subtract 3. There we go. Minus 3, minus 3. Now, because this 2 is contained within that quantity, we can't say, the 2 minus 3 is -1. So the best we can do is say x plus 2 squared minus 3 equals y. Okay, so that would be my inverse. And some people may be noticing something, and I'm going to comment on this in just a second. Okay, but here's the thing. This inverse, were we positive that he was a function? Remember, f was 1 to 1, right? So we know this guy should end up being a function. But when you finish up a problem like this, if it's a function, you're going to take y and replace it with that notation. So I'm going to say f inverse of x. But if what you end up with is not a function, then we will not replace it. We'll simply leave the y as is. Okay. Now, if you were to take a look at this, what's that the graph of? What parent creates that graph? It's a parabola, right? If I were to graph that parabola, it would be shifted 2 to the left, down 3. Okay. So it's going to look something like this. In fact, wouldn't it complete the half of the parabola that we had there? Okay. But remember, this is something important, and this is what was brought up just a moment ago. We're restricted by the domain and range that we had. Okay, that inverse can only use the domain and range that we started with. So this guy here, his domain can only be from -2 to infinity. Okay, what's his range? -3 to infinity. Okay, and that's the point that I was trying to make. You'll notice that even though we ended up with the graph of a full parabola, by using the original domain and range, we just switched them. Okay, he's already restricted, so this guy wouldn't exist. Okay, because his domain is only going to be between -2 to positive infinity. Okay, how does that? Hey. Oh, you mean actually go ahead and? You could if you wanted to. It's not necessary. I would just say leave it like that. It's perfectly fine. And, the one other thing I want to go ahead and show you very quickly, when you're dealing with a function and its inverse, okay, a lot of times you should be able to see those opposite operations. Okay, like for example, the original one, okay, had us adding 3, right? Well, what are we doing in the inverse? We're subtracting 3. Okay, over here, we're taking a square root. Here, we're squaring it. So you should always see the opposite operations. Whatever one does, the other function reverses it. Okay, let's try another one. Okay, there we go. So I got a parabola here. So let's call him something different this time. Let's call him G. This is the graph of G. And this line right here, this is y equals x. Okay, so that's the linear parent. That's my line of symmetry that I reflect things across. Okay, well, let's start with his function, g of x. Okay, well, he's definitely a parabola, but what's the one transformation that's happened? Yeah, the whole graph has been pulled down 2 units. So this is just x squared minus 2. Okay. Now, his domain would be what? How wide is he? Yeah, all reals. He's infinitely wide. So for this one, I'll go ahead and say negative to positive infinity. What about his range? He only goes from -2 to infinity. -2 included. Isn't that right, Rhett? Right. -2 to infinity. Now, let's go ahead and apply some of those concepts we had previously. If I put a vertical line through here, and let's see if I can do this without the mouse. Hey, it's actually working. If I move a vertical line back and forth, is he a function? What do you think? Yes, this guy is a function. Okay. He is a function. Okay. Let me go ahead and do the same thing for a horizontal line now. If I move a horizontal line up and down, is he 1-to-1? No. Okay. So he is not 1-to-1. So what's that tell me about the inverse? The inverse will what? The inverse is not going to be a function. Okay. And in fact, if we were to go ahead and reflect this guy, we're going to see that, yeah, he would fail the vertical line test. And maybe one thing that helps folks out, if you're having trouble seeing what the inverse looks like, maybe take some points off of the original graph and just invert them. Like, for example, we have this point right here that's a 0, -2. Well, what would that be on the inverse? It would be -2, 0. So -2, 0. So we know we're going to have a parabola that opens sideways. So probably something like that. And you can tell, if you kind of tilt your head, you can see that it is symmetrical. If I were to fold the 2 parts together, they're going to match perfectly. Well, not perfectly. I mean, my sketches aren't the best, but Okay. All right. But does that make sense? Okay. So let's go ahead and do this. I want to go ahead and find what the function is, what the equation of that inverse is. So how did we do that a second ago? Switch the x and the y. So remember, g of x this time is y. So I'm going to go ahead and separate all my information. So I've got x is equal to x squared minus 2 becomes y squared minus 2. All right, and all I want to do is go ahead and solve for y. So what's my first step? Okay, so let's add that 2. Okay. Now we will take a square root as our final step. Okay, but we want to get that 2 over first. So those are going to cancel. So x plus 2 is equal to y squared. And now that's right, we take the square root. Now when we're solving algebraically and we take an even root, what do we put in front of it? Plus or minus, yeah. Okay. So plus or minus the square root of x plus 2 is equal to y. Now, think about what we've been saying, since yesterday. We really want our inverses to be what? We want them to be functions. Is this inverse a function? No, he didn't pass the vertical line test. So will I take this y and replace it with g inverse? No. So if it's not a function, we leave the y exactly where it is. We only put the notation if it's a function. So I can't call this an inverse function. I can only refer to this as an inverse relation. Okay? I can only call it an inverse relation. Can't call it a function. Okay? And take a look. I'm going to take the original domain and the original range, and all I'm going to do is swap them. Okay? So the domain of this guy should be the range of the original. So I'm going to say from -2 to infinity. And is that how wide my sideways parabola is? Yeah, he goes from -2 to infinity, right? What's his range? There you go. So -infinity to infinity. If a parabola opens sideways, will he be infinitely tall? Yeah, absolutely. So see, it still fits. Okay. Now there is a way to guarantee that our inverse will be a function. We're going to have to restrict the domain, but I'm going to end up showing you that tomorrow. Okay, or maybe Monday. It depends on how far we're able to get. Okay. Now, I'm going to go ahead and show you one trick very quickly in case you ever have trouble seeing what an inverse will have to be. So let me draw this very quickly. I think I got, I want to use something, a darker color. Here we go. We got this blue marker right here. Okay. Now, remember, we're reflecting across y equals x, right? That's my line of symmetry. Well, if you're ever having trouble figuring out what the inverse graph looks like, okay, if you don't have any points that you can take in reverse, then do this. Okay, when you're looking at the graph, take the top left corner of your page and pull it across so that it becomes the bottom right. And you see what happened? Okay. Because basically, by pulling the top left across to the bottom right, you're folding it along that diagonal. So it'll always show you what the graph should look like over that line of symmetry. Now, fortunately, the folks at home kind of just have to listen along and imagine what I'm talking about, but you guys are here and you can experience it real time, so that makes it cool, right? Nice. All right. How are we doing so far? Is anybody having any issues? Any questions? Okay. Are you guys remembering this from Algebra 2? Good. No? But is it making sense? Kind of? Okay. That's why we're practicing. All right. Well, let's do another one. Okay. Let's try this one right here. And maybe it'll help if I go ahead and just get rid of this guy. And I just go ahead and draw. Oh, that was weird. Get rid of him. There we go. And I'll just draw y equals x by hand. It's not going to look as nice, but there you go. Okay, so let's call this function k. Okay, k of x. And really, you can name them whatever you want if they're not already named. Okay. So let's see here. First off, is k a function? See, if I were to take this vertical line right here and I start sweeping him back and forth, does he ever touch it in two places at once? Now it gets really close. This part right here, by -1, it's almost vertical, but there is just enough of a slant that he's not touching twice. Okay, so there's no value of x that repeats. This guy is a function. Okay, well, let me move that over. Is he 1-to-1? Yes. Okay, he passes the horizontal line test. Because he's 1-to-1, what do I know about the inverse? He is a function, guaranteed. Yes, Brent? Say again? Oh, I just decided to draw it this time instead of having it already up there, just to make sure everybody knew what that was, that it wasn't part of the original graph. Okay. So, let me go ahead and take this out of the way. We don't need that there. So, k of x. Does anybody know what parent this is based off of? Okay. Cube root of x, that's absolutely right. This is based off the cube root. But what's the one direction he was shifted? He was shifted to the left. Okay, so the cube root of x. We know he's been shifted 1. Now, again, would that be plus or minus? Plus. If you're shifted left, it's plus. If you're shifted right, it's going to be minus. Okay. And there wasn't any vertical shift, so we're good to go. So he is a function, but more importantly, he is one-to-one. Okay. Well, what's his domain? How wide is he? All reals. He's infinitely wide. What about his range? Again, all reals. Now, it's going to take him a lot longer to climb, okay, because he's not going immediately up like he is horizontally, but he is going to make it eventually. So he is going to be infinitely tall. So both the domain and the range are all reals. So let's do this. I'm going to first replace the y with x and the x with y. Okay. So x equals the cubed root of y plus 1. Okay. And I want you to take about a minute, rewrite this guy, solve for y. Let's see if we can get the inverse. Okay. And some people probably already have it, and that's great. Okay. But while you're doing that, it'll also give you the opportunity to start passing back some of your papers. So if you did turn in your focus activities yesterday, you're going to go ahead and get those back. And then those who turned them in today, you'll get them back probably tomorrow or Friday. Genevieve, come in. Okay. Christian, yeah, you can go to the bathroom while we're doing this. A little bit. Passes right there. Yep. Okay, Tina. Rosie, Andrew, Dolphin. Marcus. Jalen. Daniel Martinez. Leo. Okay. Right. Either would you pass that over to Deborah, please? Angel. Brandon McCormick. Rivera. Andrea. Okay, Genevieve. Fu. Andrew. Leo. Marcus. Genevieve. Rosie. Jerry. Angel. Paige. Rhett. Christian. Elizabeth. Nathaniel. Lilibet. Almost done. Daniel. Andrea. Deborah. Okay. Brendan. Was that yours? Okay. This time it was only the first name. I'm pretty sure I'd already given you yours. Okay. And then there's another Brandon. Daniel. Israel. Israel. And last up, Brandon McCormick. All right. Okay. So let's see. Can anybody tell me what the inverse is? I'm heard x cubed minus 1. Is that what everybody's getting? Let's see. The first thing I would do here, okay, I got to get rid of the cube root. So I'm going to go ahead and cube both sides. Those cancel. So x cubed is equal to y plus 1. So now I'm going to subtract the 1. X cubed minus 1 is equal to y. Perfect. That was going to be my next question. Is this an inverse relation or is it an inverse function? This one is a function. Okay. Now, if it's a function, I want to go ahead and replace y with its notation. On the previous one, remember, we left it equal to y because it was not a function. So in this case, we're calling it k. So I'm going to say k inverse. Everybody okay with that? Okay. All right. The only thing we want to do now is go ahead and reflect this guy. So if I were to reflect on this line of symmetry, y equals x, and again, I'm not real good at this, so it's probably going to look something like that. Okay. And you'll notice I tried to hit points that I knew I was going to have. Like, for example, this point right here at 0, 1 would become 1, 0. This point right here at negative 1, 0 would become 0, negative 1. And in fact, remember, x cubed does curve up to the right like that, doesn't it? Okay. And it looks like that's x cubed. All I did was shift him down 1. That's exactly the graph we got. Okay. Andrea, how we doing? A little better? Okay. Does anybody have any questions? Anybody not get the x cubed minus 1? No? Okay. All right. Let's move on to our next idea. Now, these next couple of sections, there's not a whole lot of math. It's more writing what the function is going to do. Okay, this is function notation. It says, let C of M be the cost in dollars of M ounces of mangoes. Okay. What do the following statements tell you? Be sure to use the units. Okay. So it looks to me like C of M is going to represent the cost, right? But M itself is going to be the number of ounces. So think about the relationship here. If I had an equation, the input, okay, what I plug in is going to be the number of ounces. What I get out of it, the y value, okay, that's going to be the cost, right? So think about what I'm actually saying here. If I said C of 12 equals 0.75, does that 12 represent $12 or 12 ounces? 12 ounces, okay? The original function C, okay, takes in a number of ounces and it gives you the price. Okay, so I would probably say something like 12 ounces of mango costs 75 cents. I'd probably say something along those lines. Okay. 12 ounces of mango costs 75 cents. Okay. So now look at B, where I've got C of 8 equals 0.5. So what am I actually trying to tell you with this statement? 8 ounces of mango cost 50 cents. That's exactly right. 8 ounces of mango. That's just a fun word to say. Mango. Mango. Bongo. Are you making a movie reference? No? Okay, because there's a Fallout reference. Okay, I was thinking about another movie that is hilarious, but it would absolutely not fly today. So I'll just kind of go past that. 8 ounces of mango costs 50 cents. Okay. With all the wonderful jokes I have, probably by the end, you guys are going to be like, man, go. Get it? Yeah. Hey, Brandon, what can I do for you? Why is it 50 cents? Because it's 0.5. Remember, the function C of M always gives me money. Okay. So if I have a decimal, I know that that's a certain number of pennies, so 50 cents. Okay. Or, and remember, if you go ahead and use the cent symbol, you don't want to put the decimal there. You only put the decimal if you're doing it in terms of dollars. So you could put 50 cents or like that. Okay. But you'll see some places occasionally, like when you go to businesses, you know, they might have something like that. Okay. And that's not the correct way to go ahead and write that. So the next time you're in a place like that, you could be, hey, let me help you out. I'm sure they'll be very grateful. Okay, moving on. What am I doing in C and D? There you go. We're dealing with the inverse here. So let's think about this. Originally, the function C gave me money if I plugged in the number of ounces, right? So this time, the inverse is going to give me the number of ounces if I put in what? If I put in the money. You see how I just took those two ideas and it simply reversed them? Okay, we just took the inverse. So in fact, how much money is that 3 representing? And that's $3 because there's no decimal. So I would probably say $3, okay, will buy 48 ounces of mango. 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 All right. And that's really just what I'm trying to get you to understand here. That when we take the inverse, we're taking those two ideas, whether it's the x's and the y's, or in this case, cost and ounces, and we're just switching them. Okay, the input versus the output just switches. So what would you say for D? Yeah, 75 cents will buy you 12 ounces of mango. So let's see, 75 cents will buy 12 ounces of mango. Okay, good. Okay, so let's go ahead and expand on this idea a little bit. Okay, so it's going to be a little while before we get back to some actual math. All right. Woo, that should have been covered. Okay, here we go. Pay no attention to the man behind the curtain. Did we get that reference? Wizard of Oz. There you go. Excellent. Okay. In fact, mathematically, there's still a debate today. Do you remember at the very end of that movie where the Scarecrow is given his diploma from the wizard, and he immediately puts his fingers to his temple? What's he say? He's actually quoting something in mathematics that's very famous, but he doesn't say it right. Okay, he's talking about what? Nobody remembers? Okay, well, maybe at the end I can go ahead and play the clip. But the debate is, was it a mistake made on the part of the production because they didn't know what the mathematics was behind it? Or is it speaking more to the fact that the wizard was just a hollow figure who had no real power, so he really didn't give him anything in the first place? There's an actual big debate on that in cinema. Little FYI for you right there. Okay. In fact, what time is it? 12:31? I'll tell you what, why don't we go ahead and stop here? That'd be a perfect place. Okay. You guys have done a great job today. We'll continue this tomorrow. Miss Stern will be here. I'll see if I can't encourage her to get up and interact with you guys, but we'll see what